We are ready to start. This is the last talk. Speaker is Thomas Strobl.
No, you use the ordinary title.
Yeah, but I don't remember this.
Starts bad.
It's about Christmas trees.
Decorated trees in BV and BFV, goes in BV and BFV. Yeah, something like that. Okay. Yes, so it's the honor to be the last speaker, but instead of thanking, which I will do at the end, I will complain. So you see, here, you see this year, 23. Since when does this institute exist? 18 years. 18 years it needed to be here. Such a wonderful place. And there's even another place I heard, Scaliano. Yeah. Okay. Yes, so this is a rather nice stories about the following, namely that we find, to my mind, beautiful structure in the sector of ghosts for some theories which are slightly more complicated, namely if you have a symplectic reduction which is not regular. My main example will be angular momentum in cotangent bundle of R3. You need an infinite tower of ghosts, and they can be given such a structure of trees, and there's a nice differential acting on the trees, and I will explain all this. And I gave similar talks before, but to not bore the people which actually anyway are not here and heard this talk already, I thought of going behind the scenes a bit and show how these trees arise. So it's a bit like the Feynman rules. I heard that Schwinger had actually everything there already as mathematics, but then Feynman came and reinterpreted just the formulas, and that's a bit how I want to proceed. So I will just make some calculations, and then you will see how to reinterpret them to see the structure. The other thing is that everybody tries to relate this to emergent, so that's the second task. And to please Ezra, who is certainly online, watching directly now, and Richard and his wife, Carol, they promised for Saturday evening with popcorn and beer to watch the video. So, yeah. So let's entertain them. So here are these ghosts, and then the original story was actually only in the BFV setting, but actually you can do the same in the BV setting. So I adapted my last talks from the BFV to both of them. So for any ghost, for example, this one, you can imagine, so this is a Christmas tree, as you can see evidently. There are these Christmas balls, and they have degrees. So still work? Yeah. For example, the blue ones, they have degree 1, there are 2 of them, the yellow one has degree 2, and then each vertex gives another degree. So this ghost would have degree 1 plus 1 plus 2 plus 2 is 6. And then in the BFV, you would pair them with just a copy of those. This is, I hope you can see that they are different colors. So this is darker trees and this is lighter trees of the opposite degree. In the BV, it's the same story, just to shift everything by 1. Why is that? Because they should be conjugate with respect to a bracket. So if you call the ghosts eta and the anti-ghosts pi, so this is the momenta, then this bracket in BFV has degree 0, so they have opposite degree, but in BV, the bracket has degree +1, so 6 minus 5 is +1. Okay? And the pairing is just a tree with its mirror half-Poisson bracket 1. And one of the things one obtains if you want to calculate the BFV extension of the angular momentum as a constrained system in R6, then you find this, and this continues, and one of the things is also that there's explicit recursion formulas. So this is one thing I will try to explain, and the second is from the paper of Kacztan-Felder. Yeah, I think it should be out of order. They have one example. So in the PV, you don't have a symplectic reduction, but you are given a function. So this is then just a toy model of BV, and you try to describe the critical locus of this function modulo the invariance of that same function. And the example given in the paper there is some Mexican head potential. And they say, for example, that it seems to be that there is an infinite tower of ghosts and antifields. And then also they used some program to determine like the first orders of this. And I will show you that all of these coordinates, they are trees. There's just really one-to-one. And these terms you can obtain really in a very easy way. And moreover, the computer program would need for each order more and more time, whereas we have just a recursion formula for this. Okay? So now I used introduction from a previous talk where I talk about the coisotropic reduction. So this is more or less a reminder in the beginning. So you have a symplectic manifold, you have a coisotropic submanifold, which means in physics language it's first-class constraints or the vanishing ideal forms of Poisson subalgebra. And then you can look at the leaves generated by this ideal, which is involutive and generates a foliation on this submanifold. And if everything is smooth, the leaf space itself is again a symplectic manifold, reduced phase space, so that's why I call it R, with a symplectic form. And the functions on this space can be described as Dirac observables modulo functions vanishing at that surface. So this is the Poisson normalizer. And a typical example of this reduction, but not the only one, is if you have a group action which acts on a symplectic manifold in a Hamiltonian and equivariant way, then you have a moment map, and you take the pre-image of the moment map in G0 of 0, and you quotient by the group, which is like kind of deletes two coordinates, two dimensions for each dimension of the Lie algebra. So that's why it's a double quotient, so to say. And as an example, we will take the angular momentum. So we look at rotations acting on R3. They have a canonical lift to the cotangent bundle, a Hamiltonian lift as for any lift to cotangent bundles. And the constraint surface, which you called C before, is now just on R6, putting the angular momentum to 0. So angular momentum is the vector product of x and p, or here in components where A runs from 1 to 3. And as one can see very easily, so this is not a submanifold. If, for example, x is non-zero, then p is proportional to it, and we get a two-dimensional space. But if x is 0, then p can be anything, so that has some kind of singularity at the origin. So this itself is not a submanifold, and also the quotient is not smooth. So one can ask how, in general, to formulate singular reduction. So in a more general setting, you would have a Poisson manifold, some ideal which we require to be locally finitely generated, because then any element in the normalizer, the Poisson normalizer, which is what Dirac called his Dirac observables, or not he himself, but people afterwards called Dirac observables, like those functions, small h, which the Hamiltonian vector fields of which stay inside I, if you want that the flow of such functions preserves the ideal, you need such a condition like finitely generated. It's very easy to see an example. Otherwise, you take, for example, the ideal of functions on R or R2, whatever, T star R, say, which vanish at the negative. You take the momentum, conjugate to this one variable, say, then it's in the Poisson normalizer because every derivative of a function vanishing on the left stays there, but its flow moves the zero somewhere else, so you wouldn't stay inside. But if you have this condition of finitely generated, then locally finitely generated, then everything is fine. So that's what we call an I-Poisson manifold with Hardy-Nahari. And the reduction is, again, a Poisson algebra. And if you have given a Hamiltonian, you get also a class in this quotient. And that is a Poisson algebra which you want to describe in an algebraic way in the BFV formalism. Okay, because the geometric approach doesn't work in this case. There are two examples. If you look at this smooth setting I mentioned before, then you get that this algebra, just go back, this algebra which is the quotient of this normalizer modulo the ideal, is really the functions on this reduced manifold. It induces a bracket there from the original bracket. It's easy to see, but the condition that I is a Poisson subalgebra. And if you, for example, look at the angular momentum and you look at functions being polynomials, and then one can calculate this reduced algebra, and it turns out to be polynomials on the dual of SO21. So there's no mistake in the signature. So this is a three-dimensional space. SO21 has coadjoint orbits, which are, in particular, have the light cone and then the hyperboloids around one-sheeted and two-sheeted. And the Casimir, the quadratic Casimir, is x squared plus y squared minus z squared, for example. I mean, if you quotient bait, it means you put it to zero, so you go on the light cone. So it means that the reduced phase space in this case would be the light cone, which is evidently singular at the origin. And if you work with smooth functions, you get just a forward light cone at the origin. Okay, so it's two-dimensional, but has this singularity. Then I wanted to briefly recall what you want from the BFV setting or what the BFV setting is. So you have a Z-graded manifold with a degree 0 symplectic form, which extends the original symplectic manifold. You have a charge or function of degree +1 on this graded manifold. Yes?
General reason for why this should be true? Like, you can think of the angular momentum as the action over R3 of rotations, but somehow here you're seeing a different signature.
Yeah, so this is kind of, it's a bit surprising, but it's not so surprising if you think concretely how you derive it. So you look at in rotation invariant functions on R3, T star R3, so you take x vector square, p vector square, and the inner product of x with p. Calculate the brackets, you find the SO21. Okay, but then they are not independent, so in the end of the day.
Is it an accident of this example, or is it?
No, it's in rotations in arbitrary dimension. You always find this. Mm-hmm. Okay, so there's a degree +1 function, which is that's a classical master equation, has to square to 0 in this extended Z-graded bracket, and there's also an extension of the. If it's not coming from somewhere, then there's another function h, which is an extension of the given h before, such that it satisfies a second master equation. So in the BFV formalism, there are two classical master equations, these two. And one of the main requirements one wants is that the cohomology at degree 0 and the corresponding element of this BFV extension, they are isomorphic to this reduced algebra we found before. Okay, so the strategy we will do here is like a two-step one. So we generalize it a bit more because anyway we are on the algebraic level, so we don't have symplectic manifold in the beginning. We have some Poisson algebra. written as here, some subalgebra, Poisson subalgebra I, some H in the normalizer. And in the first step, we forget the Poisson bracket. We just want to find a resolution of the quotient of O by this ideal, which is going to the submanifold, the constrained surface. And this resolution is not, has some requirement, namely we want that it's an algebraic resolution. So it needs to be some graded symmetric tensor product of some graded vector space over the original O, not vector space, module, graded module over O, which corresponds to polynomials in the ghosts, so epsilons are the ghosts. And in the second step, one reintroduces the given Poisson bracket and extends this. Actually, these are not the ghosts, these are the anti-ghosts, and then one extends by the ghosts, and one finds back this if everything works well. Okay, so the starting point for us will be, yes? Okay, BV is Bartolin-Wilkowiskin is on a Lagrangian setting, and there's an analogous story on the Hamiltonian level with Fradkin involved, which is precisely this data. So BV would the Poisson structure. Let me go. Where is it? The BV would be 1 or minus 1 Poisson symplectic form, a bracket plus 1, and so on. It's slightly different. Okay, so the starting point for us will be the following, namely, we have given this module, we have this submodule I, and we want to find first as modules a resolution. So, for example, if this ideal I is generated by polynomials, then according to a Hilbert theorem, there's always a finite length module resolution, and I will now go to two examples. So after this transparency, we go on the blackboard. So that's behind the scenes now. And I will just like do this for two examples. First to derive this model resolution, and then construct this whole tower of trees you get from there. So for this now, we should put this away. Just using the time. So, oh, mamma mia. Here. So what does it mean, a module resolution? So the homology at degree 0 would be this quotient, and otherwise the homology would be everywhere 0, just to remember. So the image of M1 under this boundary map should be precisely the ideal. Here it's mapped to 0, so that's the quotient. Okay, can we, yeah. Okay, thank you very much. So let us look at two examples. Let me start with the Kacztenfelder example. So there was some function as 0 given, which was 1/4 times the product of the function h, where h was x squared plus y squared minus 1. So here, the module we are looking at O are polynomials in two variables. And we also, here we want an ideal, and the ideal we want actually is the generators of the differential of this. So we want ds0 by dxi, so xi runs from 1 to 2. So we have xi times h. So that is the ideal. So the ideal in here is generated by xh and yh. So in the first level, M1, so we have O, map it to 0. Here we have M1. So we have two generators of the ideal. So we choose here two generators. usually denoted like this. And this can be also identified actually with the vector fields on R2 in this case, and this is just a contraction with this d as 0. And in the case if you have no symmetries of this function, so if the critical points if there's just one critical point isolated, then you can, so this would be like, as mentioned, this one shifted by -1 probably in this case. Then you could extend to multi-vector fields, and the causal resolution, if you have symmetries, this doesn't work. So you need so let's write a bit more what we have here. So we had that delta x star is xh, delta y star is yh. And now you see a very simple relation between these two elements, namely if I multiply this by y and this by minus x, I get 0. So I get one relation, which forces me to introduce here a degree 1 element. There's nothing more, so it stops here. And this beta star delta of it should reproduce this relation, so we would have y x star minus x y star. And if you reinterpret, maybe I should change the signs. If you reinterpret x star and y star as vector fields, this is just the rotations in R2, generator of rotations in R2. Okay, so here this is the example of a length 2 module. So n, capital N is 2. In principle, I want to do the same thing for the angular momentum. So let me see, maybe I don't do it in detail. So here we have O, and O here is polynomials in x1, x3, p1, p3, or xyz maybe. I don't know. No, it's fine as I wrote it. xa, pa, a equal 1, 2, 3. And the ideal, as mentioned in here, is generated by LAs. And LAs are this vector product, so there are two relations, which is the inner product with x and the inner product with y is 0. So we can get a length 2 a modular resolution. Here we first have M1, which will have 3 generators. I call them pi A. And then here we have, so we have again delta pi A is equal to LA, the generators of the ideal. And in M2, for the two relations between the generators, we get 2 elements. I call them pi and pi bar. And that's again, it stops here. And you get delta pi is, that's a convention, x a pi a, and delta pi bar is p a pi a. And you see evidently that delta square into 0 just precisely reproduces the relations in both cases. Okay, so that's these two examples. So now I want to go back to the general situation, and but with n equal 2. So I have such a resolution. And now I want to construct this modular resolution, the algebraic resolution. And first one needs to understand why one needs to do anything. And before I do this, I will just state a small lemma which we will be using to understand the situation better and actually show that we need something in the case of these examples. So the lemma is that this length 2 module resolution can be equipped with a unique commutative differential graded algebra structure. Carries a canonical CDGA, which is m dot. We have this boundary operator, a co-boundary operator, and we want a product living on this M. It's an internal product, and it should be of degree 0. That means the only thing we need to define is a product between 2 elements of degree 1, giving 1 element in degree 2, but there are some conditions to satisfy. And what are these conditions? So kind of the proof. I need a product from S2 M1 to M2, such that something is satisfied because it should be a DGA, such that so this is our product star. Here is M2. Now here is the boundary map to M1, which continues to O, and up here 0 in our case. Generally it would continue here, but this would be the first step of the general method. Then you see that you can extend D to S2M1. That's by the Leibniz rule, let's call it delta. So that's just the extension of D by the Leibniz rule to S2M1. And the condition is that this is a commutative diagram. Okay? And now it's very easy to see that there's a given 2 elements here, that there's a unique element here. How does it work? I just map with delta on this. This is an element in here, and it's closed. So if I apply another D on it, I land in 0. So because this is exact here, there's a pre-image here, and it's even exact. And that pre-image I take for the product. And then there's one more condition one needs to check, because M1 with M2 is 0, but if I apply delta on it, I'll land in M2, and that's a condition which needs to be satisfied. It follows again from the exactness of this condition. Let's calculate in the 2 examples this product. Here it's X star. Yeah, unfortunately, there are now 2 stars in the game. So this was H beta star up to a sign. Depends also on the conventions. So if I apply delta to this, I get this times H. And if I apply, if I calculate delta X star Y star minus X star delta Y star. Now you see that this is in O, so the star is certainly just the extension of the multiplication O. So this delta X star was XH, this was YH, and so this is H times XY star times delta beta star. So this is the product. If you do the same here, it's slightly more complicated, and you find, after a small exercise using the epsilon formula, this is epsilon A, B, C, P, C, pi, plus X, C pi bar, minus. Sorry?
What is the delta error from S2M1 to M1?
S2M. This one? You have a differential on M1 to O, and now this is just a symmetric tensor, so you extend it by the Leibniz rule.
Okay. And the V is what is in the example of the delta.
Just 1 second. What is the second question?
And so the V, that general notation is for this delta.
Ah, sorry, I called it already delta. Sorry.
So that's fine.
Yeah, because later we... No, you're right, it should be... yeah. Yeah, here it's still all D, but the delta will be an extension of the D. So there will be indeed delta acting on this, which is an extension of D, and actually we will need this in a second now, because you want to get this model resolution, this algebra resolution. So that was the first lemma. We see that if we start with such a model resolution, there's a unique product which is compatible with the bracket, with the differential. And we have it in the two examples. And now we start to look at the problem of this resolution. Let me look at the time. So we start like 7 minutes late or something.
Yeah.
So I have like good half an hour. Well, half an hour. Yeah. Yeah. Just to keep track. Okay, so I can delete this one. Constructing, oh, this is horrible. So we want to construct polynomials in something which will extend M1 and M2, such that this will be, so this delta is then satisfies the Leibniz rule of this, and this gives a resolution of this quotient. So we start with what we have. We have this, let's start here with O. We have M1, which we will put equal to epsilon 1. Green is bad. M2, which we call epsilon 2. But you see here, since we work now with polynomials, we also have S2 of M1. And in principle here, we may have some epsilon 3, which we would need to construct, plus S3 of M1 plus M1 times M2. So why would this be needed? Because if you have a closed element in M2, we know it's 0 in our case. However, there can be a closed element in the sum, which is not necessarily, which is not necessarily boundary, actually, which does not necessarily come from a delta, which is the extension of partial by the Leibniz rule of this. And actually, we can construct it very easily. So let us look at ZAB. which you take pi a times pi b, so this is in here, minus pi a star pi b. So this lives in here. It's closed by construction of the star product. And the question is only if it's exact or not. So if it is coming from here. And there's a very simple argument that it cannot be in the examples we have here. So if you look at the boundary map here, the boundary map, if you evaluate it at the origin, is always 0. But if you evaluate this at the origin, so this is again 0, but this is not. So it cannot be d of something from what we have. So we need something new on this place. And the construction we chose is to set this one. It's something what we want that works always, because there are some examples where, for example, you don't need epsilon 3 in a very simple case. But here we just said this is a copy of S2 M1. Now, but however, we need to shift by the degree by 1. So we just set it a copy to here. And then let us give names to the generator. So M1 is generated by pi A. Say M2 is generated by pi capital A in general. And now this is also epsilon 1. This is also epsilon 2. And epsilon 3 is now generated by pi with double index AB. And we just say that delta pi AB is the ZAB. So now this partial is equal to delta here. So maybe it was already exact, then we did too much, we would need to add this. But in any case, now this cycle is exact, and one can prove very easily, it's like a two-line thing, that now here we don't have any cohomology. Maybe I'll write it here. And now we will construct a recursive procedure. So assume, I need to delete something. Maybe I choose the angular momentum. So I will start off some level k and assume we have given already the same construction from before. So I'm at some epsilon k. I've constructed this. Here I take all polynomials of epsilon, at least of degree 2, the polynomials, which have degree k. So this above was an example. And here we have epsilon k minus 1. And we know that this here is as epsilon dot degree k minus 1 shifted by minus 1. And suppose we have given our delta already, so see that there's like a delta up and a delta down part. Delta up is linear in the module epsilon, and this goes, and delta down at least quadratic. We are given this up to level k, so it's k up, k down. Now we take another copy here, epsilon k plus 1. And we want to construct delta. So you see, here we have a map which is an isomorphism. It just shifts the degree. Let's call this map R. I could also call it suspension S, but there will be good reason later on to call this R. That's RK. Now to define delta k plus 1, delta k plus 1, we do the following. We first put this element back here. So we get RK inverse. And then for this part, we're already happy. So this is the delta down part. We just stay in here. So we take the identity here. But then we want something also here. Actually, it's needed. So what can we do? Here, however, we know already what delta does. We have the Leibniz rule. So we can apply delta to this. It ends up in these two parts, because also from here, evidently there are both of them. And we have a map also from here up there, namely RK minus 1. So what we do is we extend H, we say HK, we put 0 RK. So it's just the map which at each degree k projects out the part on the bottom, and that is sort of the extension of RK to the whole thing. And we put here minus HK minus 1 circle delta k. So that's a definition. And with this definition, two things are very easy to see. Namely, very easy to see. So if delta k squares to 0, then also delta k plus 1 will square to 0. There's like really very simple exercises. In principle, I can do them, but I want to go back to the transparencies in the example. So in principle, I can continue this exercise, but it's not needed here. There is a proposition that if you have, let me look what I wrote here. If you have if at some degree n, actually our n will satisfy this, what we had before, this for degree 2, we have hk minus 1 circle delta k restricted to epsilon k is the identity. Of course, I remind you that we just made the same, we just generalized this construction. So we had already the situation before, and if you look at delta pi AB, I'll use the microphone. It's just the identification of this pi A times pi B with this pi AB. So if I go forth and back, it's just the identity map. So then, we have a very nice formula, namely delta H plus H delta is the identity for all degrees k bigger or equal to n plus 1. So we have a homotopy. So actually, in the case n equal 2, we are done now. We proved in this small lemma that at 2 we have nothing, and at degree 3 we have a homotopy by construction. By the way, with the same argument of putting in the angular momentum example, evaluating at the origin, it's very clear we cannot have a homotopy at lower degrees, because delta is 0. Okay? But here from degree n plus 1 on, we have a homotopy. It's a very simple construction. And now we reinterpret this in terms of Feynman rules. So we add some, this green was always a bit dangerous, right? But let's try. So this pi a, we just say it's a simple tree with balls small a on them. These ones, again, simple tree with balls capital A on them. And these ones, we want to already construct out of those because it was constructed in this way. So, in fact, you see here, an element in here is actually 2 trees. And we want to get 1 tree up here of degree 1 higher. So we just make 1 tree out of this. We glue them together, add a vertex, and have a tree. So this one will be A, B. And you continue like this. You always have this S. Here is a forest of these trees. Now you put them all together, add 1 vertex, and the vertex adds 1 degree. And the total degree is always the degree of these Christmas balls plus the number of vertices. And that's it. That's the construction. Now certainly one can kind of try to re-understand the whole complex, this S dot of epsilon dot and delta directly from top to bottom, because now this was a recursive construction, but now we can say what epsilon dot is. This is just a space of all trees and so on. And that's what I'm going to explain next. So now we can go to the last part. So in principle here, I explained in general to get to get this algebraic resolution, you will need to calculate at each level a cohomology. That's the Tate algorithm, but it doesn't stop. So it's a it's then minimal what you get if you choose always the minimal number of generators at each level, but it just never stops. Whereas this procedure you saw, starting from level 3, in this case, from n plus 1, it stops and just everything is done. Nothing else to calculate. So that is our solution of this issue. So we call it arborescent or this tree-like causal data solution, where epsilon dot, that doesn't work, are m dot decorated planar trees with some symmetrization, and very good. And so this is the causal data solution of this quotient. Epsilon dot are these trees which become ghosts or anti-ghosts, and this is a forest of those trees which correspond to polynomials in them. So in more detail, so let us look at planar, at least 3-valent trees with leaves and k vertices. So for example, this would be 0 vertex, 1 leaf. At the moment, these leaves are not decorated, but now to decorate them, we tensor with n copies of the module. This will give us the Christmas trees. I don't explain it so much in detail because we had this example before. So this is a graded free O module. The resolution degree is the number of vertices plus the sum of the degrees of the leaves. And we need to take out the symmetrization because, for example, this pi a were anti-commuting. So also pi AB in AB indices needs to be anti-commuting. So If this is the right direction, yes. So this is the angular momentum example. Okay, we had it already on the blackboard, but we have like such a, we have alpha I, beta j of degrees I and j respectively, then we identify such a tree with this tree up to a sign. For example, if this was pi a and pi b, then this is just -1. So because on a plane we have a left, right, up, down. So this is well defined. It needs to be, this needs to be extended also, like if you, for example, have this inside a larger tree, or if you commute this tree like this whole branch with this branch, then you need to take the degree of the whole subtree you have there. Okay, because this has degree +1 more, so it's a +1 here. And so on. So in this way you get epsilon dot as a graded free O module of symmetrized decorated Christmas trees, and this is just then the graded symmetric algebra. So this is the forest. Also here we need a graded symmetry. So this is a graded symmetric tensor product. And now one can look back to this delta what we had. And if one looks at this procedure with R inverse, R is making a root and R inverse is unrooting, then applying delta to this tree, to this forest what you obtain, and then rooting it back, it turns out it's nothing but like for example here it's just unrooting. So we make out of these many trees just one trees. You may remember that I said delta k plus 1 is rk minus 1, and which stay there, plus something up there, which is just one tree. So this is like the forest, and then there's something if this vertex is collided to this one. So in each case you get rid of one vertex. So this in this case would give that. Then there's a second part of delta which is just applying d to the leaves. And this is true if the degrees of these leaves are at least 1, because there's one problem. If, for example, alpha is of bigger than 1, if alpha is of degree 1, or in this case, for example, gamma is degree 1, then actually here I would land in O, and this is not one of my trees. So this is forbidden. So here we get potentially a problem, but actually we had it before. Such trees don't exist, and these are just put to 0. So you formulate this as kind of Feynman rules in the game. And however, there's a third contribution now, which takes care of this first step. You remember I needed to look for this star, this product. And in general, it's not just one product, because if you have not length 2 but length n, there are several such operations I need to define. And they are no more unique, so there's a non-canonical choice, but we need to do this only up to degree n plus 1. And for n equal 2, this was precisely this operation. Take this tree, there's one contribution. If you find this somewhere as a subtree, delta 3 applied to this has the third contribution, which is precisely this product. So like you take a Christmas ball of higher degree, which is the product. So in the case of length 2, this was unique. However, in length 3, you see that here is a choice now. We can change this gamma by the boundary of something coming from M3. So there's some choice to be done, but it's finitely many in contrast to this state resolution procedure. And then there's a proposition extending this one. We had in this lemma before that any such length 2 model resolution has a unique commutative DGA. Here we have an A-infinity structure in general, which always exists, and this A-infinity structure enters the delta 3. Actually, we would like to have it like 1-to-1, but at the moment we just construct delta 3 and see there's the A-infinity. So we don't have yet a procedure to say every chosen A-infinity defines delta 3. But it would be something I would like to find. Okay, and then the theorem is that this resolution, and for the case n equal 2, I proved it to you. In general, this resolution is not minimal. For example, in the case of the angular momentum, one sees that at degree 4, we have one tree too much. But The advantage is that we have now this homotopy map, which is just like making out of several trees, one tree, if it's one tree, it goes to 0, and then we have this homotopy. And so to sum up, with this procedure, with a finite number of choices corresponding to A infinity or a bit more, we find such a causal data solution, and for starting from some degree, we have a homotopy. Now, these methods can be used for several things. For example, for the angular momentum, we not only need to intimidate you and say there's evidently infinitely many ghosts, because we can even prove it. So there are some subtrees which we can find with infinitely many vertices, and one can, with these techniques, one can show they always persist, so this never can be 0. And we can apply the same thing to this Kacztan-Feller, where they say it seems that there are infinitely many. No, we can prove it, these methods. Yeah, I probably go a bit fast here and just sum up, like, how do you construct, let me see. Okay, in the BFV setting, we now double all these trees we had before. We call one of them ghosts, the other anti-ghosts. I explained this in the beginning a bit. They have just opposite degrees. And let me drop this here. And we develop now this QBFV and HBFV in this anti-ghost number. This is the resolution degree of our tree complex, but just for not without the mirrors which the ghosts, just the anti-ghosts which we count. And then we need to solve these conditions with some boundary conditions, like, for example, that H, the 0 H extends the original H. Right? And in general, this, so that's the situation that you want to solve. So these are the boundary conditions, and this eta delta pi, so eta are the conjugate trees to the pi's. This is just such a sum over trees with its mirror, and delta, this is the original trees we had in this causal date, we just apply delta to it. So this, such an expression enters there, and then the theorem says that this always exists, and for k bigger than n, there are recursion formulas. So if I know q up to degree k, then I can use the homotopy h to get it to 1 degree higher. One needs to be a bit careful because this BFV bracket is not homogeneous in this anti-ghost number, right? Because the anti-ghost is different degrees and it just goes always to 1. And the ghosts have anti-ghost degree 0. Similar for H, and one finds also that the degree 0 cohomology is indeed what one wanted. It's really the reduction. And now the last 1 minute. We will go back to the angular momentum. So we had the degree 1 ghosts or anti-ghosts, degree 2, here at degree 3. At degree 4, for example, you see we have 3 times 2, which is 6, and this is completely antisymmetric in degree 1, so it's 1, so it gives 7. As mentioned, 6 would be sufficient, but we have a big bonus for that. And if I now applies these techniques, so up to degree 2, you have choices to take, but then from degree n plus 1, there are recursion relations, and one can reformulate also in like a more normal notation. So you see here the usual BRST charge. It's not sufficient. It's sufficient if you eliminate the origin. That would correspond to the infinity algebroid, but it has only the x coordinates, not the p dependence, and so on. In reality, it continues. And yeah, it's just the same as above, just rewritten in more normal terms. And yeah, if I add a Hamiltonian, the same story. So you have here the classical Hamiltonian. You have one part coming from here, one with the alpha coming from here, and from here on, again, recursion. So you can very easily calculated up to arbitrary degrees. And if you now go back to this Kacztan-Felder example, actually all of these ghosts and anti-ghosts are precisely the trees we have. And it's not needed to use this program to get these formulas. It just really follows very easily from this. So I started this exercise like yesterday night roughly, and so you see the trees you had. There were like at degree 1 were just 2 of them, x and y. At degree 2 we had this m2, which was just one relation corresponding to the rotations as the dual ghost. And then you see at degree 3, this is antisymmetric because they're degree 1, so it's just one tree of degree 3. At degree 4 now we have 2 trees, and at degree 5 we have those, and you can identify each of them with precisely these variables written here. And then if you calculate this here, you see that actually almost everything of this is eta delta pi, but pi is now eta star. And then there's one more term which is quadratic now here, the quadratic parts, and that would be slightly different in our formula. So here, this computer program chooses a Gröbner base to get unique results, so we get some other formula here, but one which works, and we need kind of 0 time to calculate the next order. Thank you very much.
Sometimes when there are recursions, one can package them into like a generating function or partition function type of thing, and then it becomes a functional identity. Do you think that something like this?
No, but that's a good question. I mean, for example, I showed you a recursive formula of delta and of these epsilons, and in the end, with the trees, we formulated it like we solved the recursion, right? So we try to look at the angular momentum if we see somehow some system right to construct it up directly at order n, but we didn't manage up to now at least. Yeah, so. But it would be nice to understand it better. Also, the question is, can one use these recursive formulas to calculate the cohomology, for example? Maybe a question. For example, in Kacztan-Felder, they write, okay, but with such formulas one cannot do anything because anyway, if you truncate it, the cohomology is wrong. And at each level, you need to computer to calculate the next thing. But we have this recursion, so can one use it? Probably we give some infinite sums, but maybe they give something. There's more the task, so to say, how do you see this? Because you can start with such a setting where you have sort of regular constraints, say, like x and y. You can still apply this. You get like your infinite tower of ghosts, and you want to see actually can you reduce it back to the original thing. Where, for example, you have just this causal resolution. And yeah, there are things like how to define, in some cases, minimal resolutions, how to truncate this. And one can get up to a minimal one, which we use, for example, to show that in the angular momentum, there's really an infinite tower of them. We find these one trees which are like iterated like this, which are always present in this reduction, in this reduced complex. Because as mentioned, this is not a minimal, but then you can kind of work on it more and define a minimal resolution and show that in some cases the minimal is still infinite. And in the case of like a simple one, what you mentioned, then you can just reduce everything to the like very short number of ghosts. Yeah, and as the last speaker, it's my pleasure to really thank all of you who brought us here. It was really such a pleasure, and I think we all enjoyed it enormously, so let us thank them.